In this video, I'll tell you how to make plots of light curves based on measurements that you've made of LO Pegasi's brightness by doing photometry on CCD images. So, first thing to do is to open the CSV file that you created from doing the photometry. Should be able to just double click it and have it be associated with Microsoft Excel already. And then you're going to see a warning message about if you make any changes, then they could be lost because a CSV file, being a text file, can't store all of the formatting and so forth information that Microsoft Excel can. So what you want to do is go ahead and click Save As, and then save it as an Excel file. So choose Excel Workbook star.xlsx in the drop-down under or next to Save as Type, and go ahead and say Save. So keep the file name the same except that you turn it into an XLSX file, an Excel file. There's no reason to delete the CSV file. You might want it later, so don't do that after you've done this. And then the next thing I want to do is to make all the column widths auto-fit the data. So to do that, I can click on this square to the upper left of all the spreadsheet rows and columns, selects everything. Then I can go to Format in the Home menu of the ribbon and say Auto-Fit Column Width. And so now all the columns, you can see all the full numbers or names that are in them. The next thing I'm going to do is freeze the view of the top row so that I can see the column headers no matter where I am within the spreadsheet as I scroll down on it. So for that, you go to the View menu from the ribbon, and then you can click on Freeze Panes and choose Freeze Top Row. And so now notice as I scroll through the spreadsheet, the top row stays fixed in place. I can always see it. That's very handy. You can always see the column labels. Now what I want to do is to delete rows where either there's something other than 0 for the saturated column, and that way I'll be getting rid of measurements where LO Pegasi was potentially overexposed. And the other criterion for deleting a row is if air mass, that entry is anything bigger than 2. And what that does, if you delete the row, is to get rid of data that were acquired when the star was below 30 degrees altitude, in which case there was too much atmosphere between us and the star because it was too low in the sky, and that tends to make the measurements unreliable. So notice that this very first entry has an air mass of a little bit bigger than 2, so I'm going to go over to the left edge of the row, right-click, and select Delete to get rid of it. And then I'll scroll down and look for other problems. This particular spreadsheet doesn't have any saturated other than 0 values in it. They're all good as far as that's concerned. But I do have some more air mass greater than 2 entries to delete. And the thing to notice is because when we begin our observations at this time of year, LO Pegasi is at its lowest in the sky, it's going to be the first few measurements on a given night that might have the problem of the air mass being too large. And so what I will do is go here to where we make the transition from July 7th to July 8th. Sure enough, I've got 3 entries where the air mass is bigger than 2. So I'm going to go ahead and select all 3 of those rows by going over to the left edge of the spreadsheet. And then I will right-click and delete those. And then let's see if we've got any problems when July 9th begins. So here we are on the first measurement for July 9th, and sure enough, again, the air mass is a little bigger than 0, bigger than 2. So let's go ahead and delete that row as well. Now the next thing that I'm going to do is hide columns that don't contain information that I'm going to need while I'm making my plots. So in particular, I don't need anything between saturated and CCD temp. So I hide, don't delete, but hide, because you don't want to delete them. You might eventually want this information back again. I'm going to hide those columns from saturated up to CCD temp. And then I'm also going to hide all the columns from air mass up to source AMAG T2. So in other words, air mass to source error T2 included. I'm going to hide all of those columns, not delete, but hide all of those columns. And source AMAG T2, I should mention, are our magnitude measurements of our target star. T2 stands for target 2, the second star we marked, that was LO Pegasi. So that column contains the magnitudes, the brightnesses of LO Pegasi that we're going to plot. And I'm also not going to need all these other columns when I'm making my plots, the ones to the right of source AMAG T2. So I'm going to go ahead and select and hide all of those as well. Now what I'm going to do is go up to the top row. Notice right now that I have at the top of my spreadsheet under my frozen row 1, row 59. I don't want to be in the middle of my spreadsheet, so I'm going to go all the way up to the top and then 2 columns over from the right edge of the spreadsheet. Doesn't have to be 2 columns, but I think it's nice to do it that way. That's how I like it. Anyway, now I'm going to enter some cells that contain BJD0, which will be the barocentric Julian date that is arbitrarily chosen to be time 0 for our measurements, t equals 0. And I'm also going to enter the star's rotation period. So first I will just type in BJD0 as a label in row 1 and period as a label in row 1. And then the value of BJD0, which is based on a paper written in the past about LO Pegasi that I'm trying to be consistent with. Again, it's arbitrary. That value happens to be 2455339. So go ahead and enter 2455339 under BJD0, and this will always be the case when we make spreadsheets to plot light curves of LO Pegasi. We want to be consistent there. And the star's rotation period in days is equal to 0.423075. So enter that for the period, 0.423075. Now we're going to be using the values of BJD0, BJD0, and period to calculate what's called the star's rotational phase. And we'll talk about that in a minute. But first, because we're going to keep referring to the value of BJD0 and the value of the period, it's a good idea to name those cells. So in Excel, you can give a cell a name that you can then use to refer to it. So right here, cell Z2, which contains the value of BJD0, you know that in formulas you could enter Z2 or click on Z2 and have Z2 appear in the formula, but the formula will be more readable if there's a description of what the value of Z2 actually represents. So in the name box here in the upper left of the spreadsheet, I'm going to replace Z2 with BJD0. Okay, so now notice if I click on some other cell like this one, Q6 is the name of that cell. But if I click on cell Z2, then you see that BJD0 is what shows up as the name of the cell. And similarly, cell AA2 here, and you have to be careful, don't take me literally. In other words, if your spreadsheet, you happen to have set it up so that it's in a different cell than this one, you have to click on the appropriate cell. But the cell that contains the value of the period, I'm now going to rename it as period. Okay? And so now whenever I click on that cell, period is what shows up in the name box. Now be careful. Click on, name the cells that contain the values. Don't name the cell that contains the word period. Don't name that cell period. That's not what I want. name the cell that actually contains the value of the rotation period, call that cell period. It's the name of the cell as opposed to what's in the cell that is what we're talking about here. All right, now it's time to create a column that contains the rotational phase of all of our measurements. The rotational phase is the decimal part of the number of rotations that the star has gone through since whatever time it was that you called time zero, the starting time. So if, for example, if since time zero the star had gone through 20,547.797 rotations, let's just say, then the rotational phase would be 0.797, just the decimal part of that. So in order to calculate that, what we're going to do is first we need to open up a column that will contain the values. So I'm going to click on the top of the Source Mag AT2 column here, right click, and then choose Insert. That'll open up a column to its left. I'm going to label the column Rotational Phases because that's what it's going to contain. In the first cell, I will type in the formula that lets me calculate the rotational phase. So how many rotations has the star undergone since the time that we're calling the starting time? Well, that will be however long it has been since then, divided by the rotation period. Total time elapsed over the rotation period will be the number of rotations. So I'm going to say here equals, open parenth, and then I'm going to click on this cell here, H2, that contains the time of the observation, the barycentric Julian date of the time of the observation. I'm going to subtract from that the barycentric Julian date that we're calling time zero. So that'll be the total time elapsed since that arbitrary starting time. And then I'm going to divide by the rotation period. So I will click on the cell that contains the rotation period. So notice in the formula, it says cell H2 divided by BJD0, right? So this is making it easier to read. We are subtracting off BJD0 and then dividing by the period. That's easier to read than if we had not renamed the cells and those were just cell references as opposed to name cell references. So that's the total number of rotations that the star has undergone. But remember, we only want the decimal part of that. So we take the total number of rotations and subtract the integer part of that. So the way I can do that in Excel is say minus int, open parenth, and then pick up the formula we entered for the total number of rotations. So I'll drag across that and say Control C. Then I will Control V and close parenth for the argument of the integer function, and then hit return. And we can see at this particular time, when this observation was made, the rotational phase was 0.475546889. Now that we've entered the formula in the first cell, then as usual, you can copy that down to every other cell in the column. So I will go ahead and do that now. One way to do that is click and drag. And so there we go. And now all the rotational phases of all the measurements have been calculated. Now when we plot the light curve, we're going to use different symbols for different days of observation because that can be helpful to notice, for example, if there are inconsistencies in the light curve from one night to another. That could be caused by, for example, the spots might have changed their shapes or sizes over that time interval. To make it easier not to make mistakes when we're doing that, it's very helpful to color code the entries, and so I suggest always doing that. So what I'm going to do is I go down here to where I see the very first observation on July 8th. the middle of the 3 days in this set. And I'll go ahead and go to the right and, go to the left edge of the spreadsheet and click to select that row. And then I'll scroll down and select all of the July 8th observation rows. And then I'll go to the Home ribbon and click the button that lets me change the font color. Red is fine, so it's OU colors now, right? Red and black. So I just click that, and now all the July 7th dates are black, and all the July 8th observations are red, and all the July 9th observations are black. If I had more dates, then I could keep alternating black, red, black, red, black, red, and so forth. Again, you don't have to do this, but I highly recommend it because as you'll see, when we are making our plots, it makes it less error prone. It makes it more obvious when to stop when you are picking up the data for a given date. Otherwise, you might accidentally include some data from a different date because without color coding, you have to be very attentive to the dates that are entered in the label column, in column B here. Now it's time to make our plot of the data. So if you're not there already, scroll up to the top of the spreadsheet, click on an empty cell, and then go to Insert on the ribbon, and then in the Charts box, pick Scatter Plot, like I've shown here. I don't like the way Excel likes to put the plot in front of data, so I'm going to drag it into a nicer location. And then you want to right-click in the chart area and choose Select Data. And now I'm going to make a separate data series for each of the 3 nights that are in the spreadsheet. So I'm going to click Add. And then for the series name, name your series after the date of the observations in the format year, 3-letter abbreviation for the month, and then the day. So in this case, that'll be for this first series, 2018, JUL 7. And then we're going to plot rotational phases on the x-axis and magnitudes on the y-axis. So I will bring up the selector for the x values by clicking on this up arrow. And then I can either click and drag on the rotational phases for July 7th, or I can do this. I can click on the first one and then go down and shift click on the last one, and this is where it's handy that I made the color coding of the different dates. It shows me exactly where I want to go here. And then you can close that selector, and now we can add the y values, which are the magnitudes. So I go up again, click on the first magnitude, scroll down, shift click on the last magnitude in the series, and close the selector again, say OK. Now I've added my first night of data to my plot. And then I'm going to do this for each of the other 2 nights, July 8th and July 9th, like so. So series name, 2018, July 8. Series X values, click on the first rotational phase for July 8th. Scroll down, click on the last one, close the selector. Now do the y values. First one. Last one. Close selector. OK. Now I've got 2 dates entered. One more time for July 9th. Click OK, and now that I've got all 3 nights entered, I can click OK again, and I can go up and see the plot that it has resulted from all of this. So you can definitely see that there's a nice, almost sinusoidal light curve that we've obtained for these 3 nights. We need to make some improvements to this plot. It doesn't have axis labels, it doesn't have a title, and notice that the magnitudes are plotted with larger values higher, but remember that the magnitude system is quote-unquote backwards, where lower values correspond to being brighter. So we're also going to have to reverse the direction of the y-axis here. The first thing I'm going to do is to be sure that I've selected the chart. So I just unselected it just to show you. Select the chart. And then if you're in the design area of the ribbon, and if you're not, go ahead and click design to get there. Go into the chart layouts box, and in quick layout, choose the very first entry, like so. And now let's change the chart title to something descriptive. I like to go with 2018 B, or let's go with 2018 LO Pegasi B light curve. And then for the y-axis title, let's go ahead and change that to B because these are B filter magnitudes. All right, it's fighting me here in terms of selecting the whole thing. Okay, B, capital B. And then for axis title, remember these are rotational phases, so put rotational phase for the y-axis title. And now click on the y-axis numbers, and then right-click and say Format Axis. And then in the dialog that pops out, you can change to values in reverse order by clicking this box that I'm showing here. And then you also want to say maximum axis value for where the horizontal axis crosses it, because notice right now the x-axis is up top. Let's put it on the bottom by clicking maximum axis value. So now we've got it plotted with smaller magnitudes higher, and that means that brightness increases upwards, which is what we want to have here. Now click on the x-axis values, and then right-click and say Add Major Grid Lines. And then we also want to change the way that the rotational phases go all the way to 1.2 here by default, but the maximum possible rotational phase is 1. So click on the axis, and I can say Format Axis, but notice that it had already brought up the dialog that would result. So in that case, I didn't really have to do that. But if this dialog wasn't there, you'd want to click Format Axis. And then for the bounds, we want to make the maximum be our selection of 1.0 instead of Excel's automatic selection of 1.2. And now the rotational phases are bounded properly on the x-axis between 0 and 1. And there we have it. Now we have a nice plot that shows the light curve through the B filter, has the axes labeled, has the dates labeled nicely, it's got a nice title, and the y-axis has the values in reverse order like we needed. So this is the format that I would like you to use when you're making all of your light curve plots. Of course, for the different filters, you want to change the y-axis label and the title to have the appropriate filter in it.